Okay, so in this video, I wanted to move on and talk about the brass instruments. And these are very similar to the other wind instruments in many ways, but there's some important differences that I'll emphasize in this video. So I guess the first important difference is that with the brass instruments, you don't have any tone holes. There aren't any openings other than the mouthpiece and the end of the tube that we usually call the bell of the instrument. And so in order to adjust the length of the tube to play different notes, what you have is either this slide that you have in the trombone that allows you to make the tube vary continuously in length, or you have the valves on the trumpet or the tuba or the French horn, which allow you to add little segments to the tube, depending on which buttons you've pressed, which then adjusts the length of the tube. So you have a number of lengths available to you, and then those lengths combined with being able to play many different harmonics for the particular lengths allow you to play the full set of notes in the chromatic scale over a certain range. Okay. So one important difference, so now thinking about choosing a particular length, one important difference between the brass instruments and the woodwinds that we talked about already is the shape of the tube itself. So with the woodwinds, we talked about how some cases you have pretty much a cylindrical tube like the flute or the clarinet, whereas with the saxophone or the oboe or the bassoon, you have a conical tube. Well, the brass instruments typically have a mixture of the two. So it's part cylindrical, and that is partly because if you want something like the trombone where you're sliding something in and out, it doesn't really work if the tube is changing diameter. And similarly with the trumpet and the French horn and the tuba, it's easiest to add little segments of tube using the valve mechanism if your tubes have a constant length, or sorry, a constant diameter during that part. Okay, so the bell and the conical part on a brass instrument, they have a few different very important effects on the sound of the instrument. So you may remember that with a cylindrical tube, then the natural vibration frequencies for standing waves, sound waves in the tube are the odd harmonics of a harmonic series. So you get a fundamental frequency and then 3 times that, 5 times that, 7 times that, and so forth. Whereas with a perfectly conical tube, we actually get all of the notes in the harmonic series, so F and 2F and 3F and 4F. So now we've got something kind of in between the cylindrical tube and the conical tube. So you have the cylindrical tube, which is modified at the end. And the precise shape of this modification is designed to get you most of a harmonic series. So it doesn't do as well as going to a perfectly conical tube. But what it does is it shifts the frequencies that you would have if your tube was cylindrical in a certain way. And that ends up giving you all of the harmonics of a harmonic series except for the fundamental. Okay, so you have the second harmonic, third harmonic, fourth harmonic, fifth harmonic. But then the frequency that would be the fundamental of that series is not present as a resonant frequency of your tube. There is actually one lower frequency that is a resonant frequency, so that's lower than what would be the fundamental, but that frequency is not used very much. Okay, so another aspect of the bell shape, so one aspect is just to get the frequencies in a nice harmonic series. This allows you to basically access to more tones if you can play the full harmonic series for the various lengths of your tube. It also gives you a different sound, maybe a richer sound if you are having all of these different harmonics present on top of your fundamental. And so The other reason that you have this bell shape is that it just provides a larger area for sound production. So if I play just a straight cylindrical tube, it's actually not very loud. I did that in some previous videos. So you have to play pretty hard to make a reasonably loud sound. Whereas when your tube flares outward, there's just quite a bit more area which is open to the air. And so when you have a standing wave inside the tube, and that ends up getting transferred to the end of your trumpet, and you have oscillations of the air over that entire bell area, well, that's just going to produce more sound than if you had a small end of the tube and a small area, and the oscillations were restricted to that region. So it's very much like when we talked about guitars and violins, about how the strings themselves don't produce much sound because they're very thin and they're not pushing very much air. And what you want to do in that case is to transfer those vibrations to the body of the instrument, which then has a large area and it can affect a lot of air. So here we transfer the oscillations inside the cylindrical part of the tube, which is very narrow, to this large bell region, and then you have a large area of moving air that can produce sound waves, and those are going to be at a louder volume than they would have been. One of the interesting, more detailed features of this is that particular effect, so transferring the oscillations from the narrow cylinder to the large flared bell of the trumpet, that works most efficiently for the higher harmonics, for the high frequencies. And so it emphasizes when you're playing a note and you have the various harmonics above it, the high harmonics get emphasized more because of the bell. And that gives the trumpet its bright sound, its bright tone compared to some other instruments. Okay, well, let's talk about another difference between the trumpet or the brass instruments and the woodwinds, and that is the way in which the oscillations are driven. And so we talked about how with the woodwinds you have the air jet mechanism that's used in the flute, and you have the single or double reed mechanisms that are used for the clarinet, saxophone, and the oboe and the bassoon. Well, the brass instruments, the oscillation is driven through the vibration of your lips in the mouthpiece. And the physics is not that much different from the physics of a double reed. So you can think of your lips as just being a fleshy double reed that you shove into the mouthpiece. Okay, and so like before, there's some pressure in your mouth and there's some pressure in the tube. That's varying with time. And in the end, when you're playing the instrument, when this pressure increases, at that point, your lips end up opening and extra pressure from your mouth is added to the pressure in the mouthpiece to basically support and drive that oscillation. It's a little bit different though, because in the case of the reed just sort of naturally ended up vibrating at the same frequency as the standing wave inside the tube. But your lips are bigger and heavier, and they need a little bit more help in order to achieve the right oscillation frequency. In order to kind of lock on to that standing wave frequency in the tube and support it, you need to exert more control as a trumpet player. So let's kind of understand how this works. So, you're probably familiar, even if you're not a brass player, you've made buzzing sounds with your lips. So we want to understand the basic physics of that and how it's possible to control the frequency. Okay, you can get lots of different frequencies when you're buzzing your lips. So the idea in all of these cases is that your lips are originally together, and in order to start that oscillation, you just increase the pressure in your mouth. So the pressure increases in your mouth until some point when the force from that pressure is enough to force your lips open. And then you get a pulse of air that passes through your lips. And as that pulse of air passes through, well, at that point, the pressure drops. The pressure in your mouth drops. And there's a couple of effects that cause your lips to go back together. So the first of these effects is what's called the Bernoulli effect. And that is where if you have a jet of air rushing through the lips, or really between any two objects, Bernoulli's effect says that that leads to a drop in the pressure. And you can demonstrate that just with two pieces of paper, a nice demo, where you just put them close to your mouth and the pieces of paper are apart. And then what I'm going to do is blow through the two pieces of paper and we'll see what happens. Okay. Okay, so you see that the pieces of paper actually came together. And that's because when you blow, the fast moving air ends up resulting in a lower pressure between the two pieces of paper. And so the higher pressure outside the paper will cause the pieces of paper to come together. Okay, so that is part of why the lips are coming together. The other reason, and the thing that you have the most control over, is the force of just from the lips themselves. The lips are kind of springy. If you make your lips tight and you move your lip up, you can feel that requires some force and the lip wants to spring back. Okay, and so this red arrow up and down here, it's indicating this tension force of your lips, or the springy force of your lips that wants to close them again once they've been opened by the air jet. Okay, so that Bernoulli effect, the lowering of the pressure between your lips, and also the springy forces of your lips themselves are going to snap your lips back together after a short period of time, and then we're back to this original situation. Okay. So the interesting thing is that you have a lot of control. So this is going to be a periodic phenomenon. So the pressure increases, the air jet goes through, the lips then snap back together, and then the pressure increases again, and so forth. So there's a certain period that will have, and a certain frequency of sound that's going to produce. But you have a lot of control over that. So depending on how tight you make your lips, so you just kind of add tension to your lips by making them stiffer or pulling them apart. So you can I'm sure do that. Understand that sometimes your lips are floppy and sometimes they're tight. You end up getting a much less force here or a much greater force here, and depending on how strong that force is, you're going to have the lips come back together more rapidly. Okay, so if this is a large force because your lips are tight, then this whole cycle is going to take less time, and you're going to end up with a shorter period or a higher frequency. Okay, so that's the difference between so you can adjust the frequency just by how tight your lips are. Okay, and so when you've got this mouthpiece attached to the trumpet, then, again, you can control the frequency of oscillation, but what happens is that when your lip frequency gets close to one of the natural oscillation frequencies of the trumpet tube, then it kind of locks on to that frequency. Okay, so when your mouth oscillation matches with a standing wave oscillation in the tube, then that same effect that we had for the saxophone kind of reinforces this. Okay, so when the pressure increases outside, that adds an extra force to help open your lips. Okay, and so your lips tend to open at the point when the pressure in the mouthpiece increases, and that's when the air jet goes through, and then your lips tend to close at the times when the pressure here drops. So that gives you an oscillation frequency for your lips, which then kind of matches the oscillation frequency in the tube already and reinforces that oscillation. So because you have so much control over the oscillations, then you can play many harmonics. So whereas like the clarinet, you pretty much are just using the fundamental and then the first overtone that you can play on the clarinet, which is the third harmonic, those get you all of the notes because there's so many holes, so many possible lengths of the tube. Whereas with the trumpet or the trombone, you only have a handful of different lengths that you use, so you need to be able to play a lot more harmonics. And this control that you have over your lips and the tension of your lips allows you to do that. Okay, and so you can have experienced players playing anywhere from the second harmonic all the way up to the 10th or even higher. So I'll just end by a demonstration of various harmonics being played on the trumpet. So just wanted to demonstrate various sounds you can make on a trumpet, and I can play a few of the harmonics, but then I'll have a recording of someone playing many more of them, and we'll also demonstrate some of the low tones that you could play on the trumpet. Okay, so the second, third, and fourth harmonic would sound like this. That's about the extent of my abilities, and we can go over to a recording to hear someone play the whole series here. Okay, so that was actually a C trumpet. Mine is a B flat trumpet, which is more standard. So that's why you were hearing a slightly different set of notes for the first three. So that corresponds to, as I said, you were hearing the second, third, fourth, fifth, etc. harmonic. And if you look at the frequency that would correspond to the fundamental of that series, it's actually not a resonant frequency of the trumpet. The resonant frequency is lower than that. But nevertheless, you can still play what's called a pedal tone. And so that is a note which is at the frequency of the fundamental, but it's really just a combination of all the harmonics without the fundamental being there. So here is Arturo Sandoval, a famous trumpet player, playing these pedal tones, which you'll hear on an octave below the standard notes.
Get together to be able to play those notes.
All right, so those are the pedal tones, and again, you're hearing a certain frequency, but that pure tone frequency is really not there much. What you're hearing is mostly just the second, third, fourth, fifth, etc. harmonics, and this is an example where your brain is filling in the missing fundamental. So you're hearing a frequency which is not really there very much. So there is one lower resonant frequency, lower than this pedal tone, and it's not really used. Apparently, it's not used very much by trumpet players. If you want to hear it, I've been trying to practice this. So let's just get the sound of it first. So it's supposed to be around 90 hertz. So it'd be like this. Okay, and so we'll just give that a shot. All right, so I think that was it. Who knows why they don't use that one in the orchestra more?